Hello everyone, welcome to our lecture on digital logic design. I'm Dr. Vilayat Khan. The major topic of today's lecture is combination logic with MSI and LSI. The subtopic is magnitude comparator. In today's lecture, I will design a magnitude comparator. A magnitude comparator is a logic circuit that compares two numbers A and B. This kind of circuit is very useful in calculators and in computers for the logical operations to compare two results, two values. So let's suppose we want to compare two numbers, then we may need to implement or use a magnitude comparator. A magnitude comparator just compares two numbers A and B, and the outcome of the comparison is either A is greater than B, or A is equal to B, or A is less than B. So these are the three possible outcomes of a magnitude comparator. It will tell us the relation between the two numbers A and B. A magnitude comparator, just like many other combinational circuits, can be designed in two different ways. The one is the most popular one is the classical method, where a K-map is used, and another procedure is algorithmic procedure, where a new algorithm has to be designed or derived, and then an MSI circuit, an existing MSI circuit or LSI circuit or a package is used to implement a magnitude comparator. And the classical method, if we use the classical method, then for an n-bit comparator to design, we must need to have 2 into 2 raised to power 2n entries. Let's suppose we want to design a 4-bit magnitude comparator, then that would mean that the magnitude comparator would take two numbers, and each number is a 4-bit. Then in total we would need 8 inputs, and that in turn mean we would require 8 variable maps, and that would require 2 raised to power 8 entries in the table, in the truth table. So in case of 4 bits, we would need 256 entries in the table. That means 256 rows in the truth table and 8 variable k-maps to simplify the corresponding Boolean functions. So obviously this is not very simple to write such a large table on the paper and then use 8 variable k-maps to simplify the corresponding Boolean function. So as alternative, there is algorithmic procedure which we have already used in the BCD adder example. Any circuit that has a regular pattern can be implemented using an algorithmic procedure. So in today's lecture, I'll design a magnitude comparator, and I'll be using an algorithm to implement the magnitude comparator. So to think about in that direction, we must understand what or how the two numbers would look like. So for example, if we want to derive a Boolean equation for the first operator, that is A is equal to B, when the outcome of the magnitude comparator is A is equal to B, then we have to split the two numbers into their bits. For example, we want to compare two numbers and they are 4-bit numbers. Then A is 4-bit number and B is also 4-bit number. Then the 4 bits of these two numbers would be designated as A0, A1, A2 and A3. Similarly, the 4 bits of the other number B are B0, B1, B2 and B3. These subscripts represent the significant position of these bits. So the bit A0 is the least significant bit, and A1 is the higher significant bit, and A3 is the most significant bit. Similarly, B0 is the least significant bit and B3 is the most significant bit. So these are the 4 bits of number A, and these are the 4 bits of number B. So if we are talking about when A is equal to B, when we can say that A is equal to B, for that, if the corresponding bits of number A and number B are equal, then we can say that A is equal to B. In other words, for these two numbers with 4 bits, if the bit position as 0 at A0 and the other bit in number B at B0 are the same, as bit A0 and B0 are the same, if both are 0 or both are 1, and the same is true for the next higher pair of bits. A1 is equal to B1, A2 is equal to B2, A3 is equal to B3, then we can say that all the corresponding bits of A and B are equal, so we can say that A is equal to B. The number A is equal to B. Logically, when we say that two bits are equal, then either both of the bits are 0 or both of the bits are 1. So in both cases, we can say that the two bits are equal. Logically, there is an equivalence function to state this condition when the two bits are equal, and let's suppose that condition is xi for a particular significant position, and that's why we use the subscript I, that I can be 0, 1, 2 or 3. Then the equivalence function is ai dot bi plus ai prime dot bi prime. So this is the equivalence function. The value of whenever the value of xi is 1, then the bits at position I are equal. For example, let's suppose ai and bi are both at 0, then this term would result 0 because ai dot bi 0 dot 0 is 0 plus which is the logical OR operator, ai prime bi prime, this would give 1 because ai is 0, so 0 with a prime is 1, b is 0, so bi is 0, so bi prime is 1 again, so 1 dot 1 is 1. So in either case, whenever the value of ai and bi are the same, or if they are both zeros or if they are both 1, then this function would give 1. The value of xi would be 1. So this equivalence function exactly determines if the two bits at a particular position represented by I are equal or not. This logical function represent the equivalence at particular significant position. So if we want to identify if A is equal to B, then we must ensure that all the bit pairs of the two numbers at all significant position 0, 1, 2 and 3 are equal. So this equivalence function calculates the equivalence of two bits at a particular position, and if we do the same for all significant positions, then and if all the bits are equal, then we can say that A is equal to B. Logically, if we want to state that A is equal to B, let's suppose A is equal to B, this is a Boolean variable. We could have used a single letter variable as well, but this variable A is equal to B is more meaningful, so we are using A is equal to B. So A is equal to B if the two bits at significant position 0 are the same, and also if the two bits at significant position 1 are also the same, equal, and if the two bits at significant position 2 are also equal, and if the two bits at significant position 3 are also equal, and there is a dot operator, so we are using the term AND. So we say that if all the bits at all the significant positions are the same, then we can say that A is equal to B. So logically we have actually derived a Boolean equation, and this Boolean equation states that when a is equal to b. We can later on replace these x0, x1, x2, and x3 with corresponding Boolean function. For example, x0 would be equal to a0 dot b0 plus a0 prime dot b0 prime enclosed in parentheses, then dot, then x1 would be equal to a1 b1 plus a1 prime b1 prime, and similarly for x2 and x3. So we have calculated or derived the Boolean equation for a is equal to b. For comparing two numbers and deciding about if a is greater than b or a is less than b, we must compare the relative magnitude of pair of bits at the most significant position. We have to start from the most significant position, and then we have to move on the right direction and do the same for all other significant position. So we have to begin at the most significant, at the pair up at the most significant position, and to compare them. And if they are equal, then we have to compare the next pair of bits on the right side. But we have to begin at the most significant position, the pair at the most significant position. We have to compare them. If we want to find out if a is greater than b, then the pair at the most significant position of the two numbers must be compared with each other. If a3 is greater than b3, we are comparing the bit position at significant position 3, which is the most significant position in 4-bit when the numbers are 4-bit. So we are comparing a3 with b3. If a3 is greater than b3, then we can say that a is greater than b. In other words, if a3 is 1 and b3 is 0, this is the only possible way when a3 is greater than b3. When a3 is 0, a3 is 1 and b3 is 0, then we can say that a3 is greater than b3. Logically, we would like to have the outcome 1 for this condition. So we can state this condition like this: a3 b3 prime. So this term would result 1 when a3 is greater than b3. How? Let's suppose a3 is 1 and b3 is 0. So a3 would give 1 dot b3 is 0, so it would also give 1 because of the prime. So 1 dot 1 is 1. And in all other cases, it will give us 0, because if a3 is 0, then 0 dot anything is 0, so it would give us 0 if a3 is 0. If a3 is 0 and b3 is 0, then in both cases, regardless of the value of b3, if a3 is 0, then this term would give us 0. So if a3 is 0, then this means either a3 is equal to b3 or a3 is smaller than b3. In both cases, it should return 0. It would only return 1 when a3 is 1 and b3 is 0, which is what we need. Okay, so if a3 is greater than b3, then we can declare that a3 is greater than b. But this may not be the case. For example, if the bits at the most significant position are equal, for example, a3 is equal to b3, then the bits at this position cannot tell us if the relation between a3 and b, the relation between number a and b. So what we have to do is we have to check the next pair of bits at position 2, and we can logically state in this term, that is x3, which is a logical equivalence relation, and x3 means that the bit position, the bits at significant position 3 are equal. Dot means and a2 b2 prime means the bits at next position a2 is greater than b2. That is, a2 is 1 and b2 prime is b2 is 0, so b2 prime would give us 1. So this term, whenever this term gives 1, This means that the bit position at most significant are the same. The bits at the most significant position are the same, and in the next pair, A2 is greater than B2. That is, A2 is 1 and B2 is 0. So this term would tell us if number A is greater than B or not. If the bits at the second position at significant position 2 are equal, then we have to move to the next pair of bits on the right, and to continue with that, we would come up with a Boolean equation like this. So A is greater than B when either A3 is 1, B3 is 0. A3 is the bit at most significant bit position, and B3 is the bit at most significant position of the other number. So A is greater than B if A3 is 1, B3 is 0, or the bits A3 and B3 are equal, and A2 is 1, B2 is 0, or the bit at position 3 and position 2 are equal. That means the bit pair at significant position 3 are the same, the bits in the pair at significant position 2 are the same, and A1 is 1 and B1 is 0. If this is the true, then we also declare A is greater than B, or the bits at significant position 3 are equal, and the bits at significant position 2 are equal, and the bits at significant position 1 are equal, and A0, which is the rightmost bit, is 1 and B0 is 0. Then also we can say that A is greater than B, and this is the condition for 4-bit numbers. So A is greater than B if either of these terms result 1. So we have derived the Boolean equation for A is greater than B, and similarly we can proceed. We can derive the Boolean equation for A is less than B. So quite similar to the A is greater than B, we must compare the bits at most significant position first, and if they are equal, then we have to compare the bits, the next pair of bits on the right side. So if A is less than B, if A3 is less than B3, if we are talking about the bits at most significant position, then if A3 is less than B3, then we can say that A is less than B. That is, if A3 is 0 and B1 is 1, A3 can only be less than B3 if A3 is 0 and B3 is 1. Then we can say that A3 is less than B. So we can then declare that A is less than B. And logically, we can write it like this: A3 prime B3. So this term would give us 1 whenever A3 is less than B3. So when A3 is less than B3, then A3 would be 0. So 0 would give 0 prime would give 1, and B3 is 1. So 1.1 would give us 1. So when this term would give us 1, then that would tell us that A is less than B. But if the bits at the most significant position are equal, then again we will not be able to identify if A is less than B. So we have to check the next pair of bits at position 2, and we would also indicate that the bits at significant position 3 were equal. So to combine the two, just like we did before, we would say that x3, which tells us that the bits at significant position 3 are equal, and A2 prime B2 means A2 is 0, B2 is 1. So A2 is 0, B2 is 1. So if this term gives us 1, then it would also mean A is less than B. and if the bits at significant position 2 are equal, then we have to move right one step further, and we have to look to compare the bits at significant position 1, and similarly we have to continue for all other significant positions on the right side, and finally we would come up with this equation. So we do this for all 4 bits. A is less than B is equal to A is less than B if A3 is 0, B3 is 1. When A3 is 0, B3 is 1, then obviously A3 is smaller than B, or if this is not the case, or if the bits at significant position 3 are equal and A2 is 0, B2 is 1, then also we can say A is less than B. Or if the bits at significant position 3 are equal, the bits at significant position 2 are equal, and A1 is 0 and B1 is 1, then also A is less than B. Or if the bits at significant position 3 are equal, the bits at significant position 2 are equal, the bits at significant position 1 are equal, and A0 is 0 and B0 is 1, then we can also say that A is less than B. So this comparison of the bits at different position is done for all the bits, and in our example A is a 4-bit number, B is a 4-bit number, so we compare the bits at all 4 significant positions. So we have derived 4 Boolean equations for the 3 Boolean equations for the 3 variables. A is equal to B, A is greater than B, and A is less than B. To further refine the equivalence function, that you would need this to make an efficient implementation of the magnitude comparator. We can write that AI bi plus AI prime bi prime is equal to AI prime bi plus AI bi prime whole prime. This is exclusive OR operator, and we can reuse these terms as the term like this have been used in the Boolean equations of the magnitude comparator. So this would give us advantage to reuse a number of logical AND gates. But one question arises: how can we say that these two Boolean terms are equal? We have already done similar. We have already derived similar equations before, and just to remind you, if we had designed a half adder where we calculated or derived the Boolean equation of S by combining the minterms in where the output was 1. So that gave us x prime y plus xy prime, and if we include or combine the minterms where the value of S is 0, then that would give us S prime. So when we combine the minterms where S is 1, then that would give us x prime y plus xy prime. This is the exclusive OR operator, exclusive OR operation. And when we combine the minterms where the value of S is 0, then this would give us xy plus x prime y prime. But this is the complement of S because we have combined the minterms where the value of S is 0. So we got these two equations 1 and 2, and when we put the value of S from equation number 1 in equation number 2, then we get this. So S, we get x prime y plus xy prime whole prime, and on the right side we have xy plus x prime y prime. So this is equation number 3, which is exactly similar to this equation, but just the variables are different, and in our case we are using AI bi, so that's why we can say that AI bi plus AI prime bi prime is equal to AI prime bi plus AI bi prime whole prime. So they are syntactically the same. Okay, so I hope this is clear. So we would be using this equation in the implementation of the magnitude comparator with the logic gates. Okay, so let's begin with the implementation. Okay, so first we implement the Boolean function a is equal to b, which is x0, x1, x2, and x3, and each xi is actually an exclusive OR with exclusive NOR operation actually. So x0, for example, is here where x0 is a0 dot b0 prime, a0 prime dot b0 prime, and this NOR gate actually implements the whole complement which was above the parenthesis. So actually this part implements x0, this part implement x1, this part implement x2, and this part implement x3. The other connections are used for the a is greater than b and a is smaller than b equations, which we will see shortly. So this is actually an AND gate which combines x0, x1, x2, and x3, and this would tell us if the value of the output at this line is 1, then this would tell us that the number a and b are equal. Similarly, we can implement a greater than b, and here we can see the same equation that we have just derived. So a3 b3 prime, a3 b3 prime, this line comes from a3 b3 prime, a3 and b3 prime, which comes here and is given as an input to this OR gate. And then the next term is x3 and a2 b2 prime. So this is the line, so we get x3 from here, and the next term is a2 b2 prime, a2 b2 prime. So this term we get here and is given as input to this OR gate, and similarly for other terms, and we get a greater than b. So if the output at this line is 1, then this would tell us that a is greater than b. And similarly for a smaller than b, we implement the same Boolean equation, and this Boolean equation is quite similar to this one. Just for one per term like this, this is a3 prime b3, a3 prime b3. So the connection from the upper AND gate is taken, and for the a greater than b, the connection from lower AND gate is taken. So that is the difference. x0, x1, x2, and x3 are used in all functions, so they are the same. So this is the implementation of magnitude comparator with logic gates. To combine all these gates in a package, we would get this block diagram. So this is 4-bit magnitude comparator. In this 4-bit magnitude comparator, we get the 4 bits of number a, where a0, a1, a2, and a3, these are the 4 bits, and we get the 4 bits of the other number b0, b1, b2, and b3, and we get 3 outputs. One output tells us if a is equal to b, the other output tells us if a is greater than b, and the third output tells us if a is less than b. And one thing must be noted, and that is that at one time either of the 3 outputs is 1. So only one output is 1 at that time, the other 2 outputs must be 0. So for example, if the output at this output at this line is 1, then a is equal to b, and if the output at this line is 1, then a is greater than b, and if the output at this output, the value at this output is 1, then as less than b. Similarly, okay, so this is a 4-bit magnitude comparator. For further reading and questions, please refer to the textbook Digital Logic and Computer Design. All the details, further details are given in this book by Maurice Manu. And also, please read the presentation slides that have been shared. Also, to be more clear during the online queries, please keep a note of queries that you want